Hey everyone, and welcome. Today, we're going to dive into the physics behind something we feel every single day, but honestly, often get wrong: temperature and heat. It turns out these two concepts are the invisible force that drives pretty much everything, from our weather to the technology in our pockets.
So let's kick things off with a little puzzle. What could possibly connect that gentle, cooling breeze you feel at the beach with the super hot, controlled explosion that powers a car? I mean, they seem like they're from completely different worlds, right? But as you're about to see, they're really just two sides of the exact same coin.
All right, so let's get into it. We're going to take apart these two everyday things to find that hidden thread that ties them together.
Okay, first up, the sea breeze. Picture this. On a sunny day, the land just soaks up the sun's energy, and its temperature shoots up way faster than the huge ocean right next to it. And that one simple fact kicks off this massive all-natural air conditioning system. And then you've got the car engine. This thing is an incredible piece of engineering. It takes the chemical energy that's locked inside gasoline, turns it into this intense burst of heat through combustion, and then uses that heat to create the physical force that actually makes the car move. So, the secret that connects them? It's buried in the difference between two words we use interchangeably all the time, but which mean totally different things in physics: temperature and heat. Getting this difference is the key that unlocks everything.
So let's get really precise here. What are temperature and heat, really? This is the absolute core of our whole explainer.
Temperature, it's all about motion. Just think of it like a speedometer, but for the teeny tiny atoms and molecules that make up everything around us. When you measure the temperature of something, what you're really measuring is the average speed or kinetic energy of all its little particles. The faster they're zipping around, the higher the temperature. It's a property of the thing itself.
Heat, on the other hand, isn't something a substance has. Heat is energy on the move. It's the flow of energy that happens, and this is key, only when there's a difference in temperature between two things. Energy always flows from the hotter object to the colder one, from the faster particles to the slower ones.
And this is where it all kind of clicks into place. Temperature is a measurement, right? A property. We measure it in degrees Kelvin or Celsius. But heat is the transfer of energy itself, and we measure that in joules. So here's the bottom line. A hot cup of coffee has a high temperature. As it cools down, it's losing energy in the form of heat flowing out into the room. Okay, so we've got the theory down. Now let's circle back to our original mystery and see how this flow of energy, this heat, can actually do work and create real motion in the world. So back to that sea breeze. Because the land heats up so fast, the air directly above it gets hot too. And what does hot air do? It expands and rises, creating a pocket of low pressure. Meanwhile, the air over the cooler ocean is denser, creating high pressure. Well, nature doesn't like that imbalance, so that cool, high-pressure air rushes inland to fill the gap. That rush, that's the sea breeze you feel. It's literally wind created by heat transfer.
Now the engine, it uses the same exact principle, just in a much more, explosive way. The magic all happens in that third step, the power stroke. After the fuel and air are squeezed together, a spark ignites it. Boom! This combustion releases a huge amount of heat energy, which makes the gas temperature and pressure inside that tiny cylinder skyrocket. That super high-pressure gas expands like crazy, forcing the piston down, and that's the work. It's a direct conversion of heat into motion.
But here's a question. How good are we at actually capturing all that energy? You might be shocked to hear this. A typical car engine is only about 20% efficient.
Just think about that. A whopping 80% of the energy from the gasoline is just lost. It's vented out as waste heat through the exhaust and the radiator, or it's lost to friction. You know why your car's engine gets so hot? It's because it's literally throwing away most of the energy it's creating. It's a pretty powerful reminder that even though we can harness heat, controlling it efficiently is a huge challenge. And that whole challenge of efficiency, it all comes down to being able to control that energy transfer. So, how do scientists actually measure and predict that flow of energy? Well, it turns out there are some pretty solid rules they follow.
To measure temperature, we've got our usual suspects, right? Celsius, Fahrenheit. But in science, Kelvin is really the standard. And to calculate the heat that's been transferred, we use this beautiful little equation, Q equals mc delta T. It just tells us that the heat, Q, depends on the object's mass, its specific heat capacity, which is just a fancy term for how much energy it takes to heat it up, and, of course, the change in its temperature.
So let's make that real for a second. Let's say you have a 2-kilogram chunk of metal.
and you heat it up by 30 degrees Celsius. If you know its specific heat capacity, you can plug in the numbers and find that it absorbed exactly 24,000 joules of energy. It's not magic, it's predictable, it's physics.
So let's pull back and just look at the big picture for a moment. This stuff isn't just abstract physics in a textbook. It's basically the fundamental operating system for our entire world.
So what are the big takeaways here? 1. Temperature tells you how fast particles are moving. 2. Heat is the energy that flows because of a difference in that motion. 3. That very flow of energy is what creates work, driving everything from global weather patterns to the very device you're watching this on. This is the heart and soul of thermodynamics.
And that leaves us with one last and really critical thought. This same process of heat transfer that powers our entire civilization is also, through waste heat and emissions, the engine behind climate change. So the challenge for our future isn't just about using energy, it's about mastering its transfer way more efficiently. How can we design systems that do more work with less waste? That's a puzzle for all of us to think about.